In the previous two videos, we discussed physical, thermal, and electrical failures, but now we delve into a less visible but equally critical dimension: software. Modern inverters are no longer black boxes with electronics. They are digital systems with firmware, control algorithms, and communication protocols that depend on SCADA. And like any digital system, they can fail. The worrying thing is that when they do, the impact isn't always immediately detected. There's no smoke, no sparks, no blown fuses. But the inverter starts behaving strangely or simply stops communicating, and this compromises the entire plant supervision. Recent technical studies have detected more than 40 errors related to software bugs, update errors, communication failures, version incompatibilities, and memory corruption issues. These errors generate very specific operational consequences. The plant can completely lose connection to the SCADA. The inverters can enter suboptimal mode, especially in MPPT tracking, and all of this can go on for days without a clear alarm being triggered. For maintenance, this represents a significant challenge because there is no visible alert. Often, the only noticeable drop is a slight but persistent drop in production. Detecting this requires reviewing logs, intervening with remote support, or even physically reinstalling the firmware. Sometimes, the entire controller board must be replaced. From a financial perspective, the loss of communication is especially critical. Without SCADA, real-time monitoring is impossible, physical failures go undetected, and the ability to react to the market is lost. But more importantly, a logical failure can cause an inverter to generate less energy for weeks without anyone noticing. These losses accumulate, go unreported, and in the long term, erode the project's ROI. Why it's key to have a well-defined update protocol, conduct pre-testing in controlled environments, and maintain stable copies of the firmware. It's not just about technology, it's about protecting the operational and economic continuity of the plant. Because software, even if it leaves no physical trace, can be the source of the most silent and costly losses. Now let's analyze a category of failure that, while not causing burnt components or obvious physical damage, has critical consequences at both the operational and financial levels: grid synchronization problems. This type of failure often goes unnoticed because it doesn't involve a visible breakdown, but it generates immediate production losses and can result in significant financial penalties. We quote, talking about automatic inverter disconnections caused by deviations in parameters such as frequency, voltage, or grid signal quality. According to the IEE 1547 standard, which is mandatory for grid connection, inverters must operate within a strict frequency range between 49.5 and 50.0 MHz, with voltages within plus or minus 10% and a harmonic distortion, THD, level of less than 5%. When these limits are exceeded, inverters disconnect to protect the grid, but this means they stop generating power immediately. And that's the problem. These disconnections, often due to misconfiguration, a lack of updates, or a grid disturbance, not only disrupt production, but can also trigger penalties. PPAs or service level agreements, SLAs, often include strict clauses regarding energy availability and delivery, and any unjustified interruption can result in financial losses. Furthermore, if multiple inverters disconnect at the same time and share the same substation, a domino effect can occur, further exacerbating the impact. From a maintenance perspective, this type of failure requires a preventive approach: constant verification of grid parameters, real-time monitoring, and automatic firmware updates with the latest evolutionary codes. It's not enough to simply install it and forget it. Regulations change, thresholds can be adjusted, and if the system isn't adapted, disconnections will continue to occur. The important thing here is to understand that this failure is invisible, but it is costly. Every hour of downtime can represent thousands of euros lost, both in ungenerated energy and in contractual penalties. And in a utility-scale plant, these figures escalate rapidly. Therefore, in the era of dynamic codes and smart grids, those who fail to monitor and update will inevitably be disconnected. Here's a summary of everything we've been analyzing throughout these videos: the most common types of inverter failures, their frequency, the technical impact they generate, the mean time to repair, MTTR, and most importantly, the financial consequences they entail. We're not just talking about a technical representation, but a strategic tool that combines operational data with clear financial implications. Understanding this matrix allows us to make informed decisions that have a direct impact on the profitability of a photovoltaic plant. Let SE take IGBTs as an example, which appear to be the most critical component. Not only do they require more than 4 hours of intervention on average to repair, but their associated costs are also high. Each failure can generate losses exceeding €12,000 per megawatt per year. Although they are not the most common components to fail, each incident is so significant that it requires planning for specific spare parts and employing highly qualified personnel. They are the type of component that, if not handled strategically, can make the difference between a profitable plant and one accumulating losses. At the other end of the spectrum are fans. They tend to fail more frequently, but the individual impact is less. However, their accumulation over time ends up having a considerable impact. Therefore, the strategy changes. It is not about preparing for a major one-time intervention, but rather about having a constant preventive maintenance cycle in place that allows us to act before the accumulation of small incidents leads to a reduction in the inverter's overall efficiency. But not everything is related to physical parts. There are other types of failures that can go more unnoticed, such as software errors. These don't always trigger obvious alarms, but they affect inverter performance, maximum power point tracking, MPPT, or communication with the SCADA system. These are silent failures, but potentially very costly if they persist over time without being detected. Therefore, log monitoring and proactive monitoring of the performance of digital systems is a key component of the maintenance plan. Then there is the issue of grid synchronization. This type of failure, although less frequent, can automatically disconnect entire blocks of inverters if certain voltage or frequency thresholds are exceeded. The problem is not only technical, it is also financial. It often leads to penalties, loss of energy delivery guarantees, and a direct impact on a PPA's revenue. These are failures with low MTTR but extremely high economic impact. Therefore, they must be managed with the same priority as any critical component. All of this translates directly into the plant's economic variables. The average MTBF of 1.65 years means that an inverter, on average, fails every 20 months. This implies a frequency that, if left uncontrolled, generates a cumulative increase in O&M costs. It is estimated that these failures can increase operating expenses by more than 23%. In other words, a utility-scale plant can be losing between €100,000 and €500,000 annually simply by not adequately anticipating these failures. Therefore, this matrix is not simply a visual summary or a technical diagnosis. It is a prioritized guide that helps us focus resources where we will obtain the greatest return. If the objective is to reduce losses and optimize production, the strategy cannot be based on intervening in the cheapest or most visible areas. We must start with what weighs most heavily on the financial balance. And that's where technical and financial profiles must work together, using this type of analysis as a common basis for decision-making. This intersection between engineering and finance, between maintenance and strategy, is the true value of this image. It's not enough to simply repair quickly or have smart sensors. What truly transforms an operation is knowing where to invest first, why, and what the expected impact might be. And this matrix gives us that roadmap to act intelligently and efficiently.